Hello there, folks. I hope you're doing well. In this video, we are going to be talking about Chapter 4.2, Maximum and Minimum Values. I'm going to need you to follow along in your textbook for this video, so please turn to page 171 of your textbook. When we're talking about maximum and minimum values, we are going to need some definitions. So, in general, a function f has an absolute maximum value at a point C if f at C is greater than f at x for all of the other x or all the x in the domain of f. And the number f of C is called the maximum value of f. I think I just misspoke somewhere around there. But basically, if it's the highest, if you have the highest y value, that value of x is the maximum value, is what it's saying. And then there is also an absolute minimum value for the opposite, where the y value is the least across your entire domain. The extreme values of the function f are the maximum and minimum value. So if I'm talking about extreme values, I'm talking about absolute maximum and absolute minimum. However, if we switch over to the next page, we can also have local maxima and local minima, or a relative maximum and a relative minimum. These occur when I have a little blip. So turning back once again to 171, if we look at, say, the point 4.5 or 4.5 and the point 5.3, 4.5 is a local maximum. If we restrict the domain to be between, say, x is equal to 3 and x is equal to 4.5, that is going to be a maximum. Or, right after that, we have 5.3, which is going to be a local minimum. But over the entire function, the absolute maximum is at 0.76, and the absolute minimum is at 0.21. Example number 1 has a few drawings there, or a few graphs there. So we have, first of all, a quadratic, so just an x squared. So let me try my best to draw an x squared. It might not turn out so well, but yeah, you can sort of tell it's an x squared. And then I do have an x cubed, which looks something like that. Something like that. We'll call that good. So at x, if we look at x squared first, you can see that x squared does have an absolute minimum value, as well as a local minimum value at this point here, x. However, it does not have a maximum value. It goes up toward infinity. Infinity does not have a value, so we cannot say that it has a maximum value. So, min, but no max. For x cubed, we have neither. We are going into negative infinity and positive infinity, so we have no min nor max. We have no min nor max. Example number 2. That's example number 1 and example number 2. Example number 3 now has a new function. We have the function 1 minus x squared between the values of 0 or x values of 0 and 1. So if we do that now, it's going to look something. Draw my graph once again, or my axes once again. So it's going to start here at 0 and something like this. And this here is at point 1. However, it does not include 1. It has a maximum value. But because the point, even though it tends toward the x-axis, or in other words, it tends towards y equals 0, max, and I'll just say 0, 1, because this is at 1. It tends towards 0, but it never actually reaches 0, because we can go further and further. We could, 1.01, 0.1, 0.01, 0.001. Since there is no end, once again, much like when we went to infinity, we do not have a minimum value. We can just get closer and closer to 0. So for a case like this, we have no minimum value. And if we look at a, not similar, at a different graph, so this one was 1 minus x squared. This one is x cubed minus 3x, and we got to have a domain as well. So 0 is less than or equal to x, and this one, the domain x is greater than or equal to negative root 3, which seems like an arbitrary number, but that is the point where this graph actually crosses the x-axis at this point. However, it is a cubic function, so it goes up here and then crosses at 0, 0, has a minimum, and goes up toward infinity up there. So we have a couple of points that are important. We have it cross the x-axis at negative root 3, 0. It has a local maximum here at negative 1, 2. A local minimum, sorry, this is just an absolute minimum. The left side, the endpoint, the first endpoint, negative root 3, 0, would be a local minimum. But it's also the endpoint of the graph. And we have an absolute minimum here at 1, negative 2. But there is no absolute maximum because the graph goes on toward infinity. So we have a local maximum, an absolute minimum. We have an endpoint, which could be, in theory, a local minimum if we just look at things up to a certain point, if we restrict the domain further. But there is no absolute maximum in this function. So we see from these first 4 examples that, this was example 4. 4, 3. There we go again, throwing in two at a time. We see from these examples that a function doesn't have to have maximum and minimum values. But there is a proof that any continuous function that is defined on a closed interval, that is, if we were doing it with circles, the circles are all filled in, and it has an end. There's none of this stuff up here. Or if we were doing it with the brackets notation, it's in square brackets. Or if we're doing it in the other notation, it's always less than or equal to something. Then there is going to have an absolute minimum and an absolute maximum. That's just how it works if we have a closed interval. If we have an open interval, that's not going to be the case. If we do not already know what the graph of a function looks like, since we have graphing calculators now, it makes it way easier. We can try and find out the maximum and minimum values by looking at we could figure this out by looking at the tangent lines on the graph on page 173. If you look, that every local maximum and minimum value, or most of the local maximum and minimum values there, do have a slope of 0. For points D and E, there is no slope of 0 there because because of that shape, that very sharp shape, that's telling us that there's an absolute value involved there. And when an absolute value is involved, there is no derivative, or no tangent. There is no tangent in that point, anytime that there is a sharp corner. Which leads us, hopefully that was sensible, I apologize if it wasn't, which leads us to Fermat's theorem. If a function f has a local minimum or maximum, max or min, at C, then the derivative of f at C is equal to 0 or is undefined. Now, it doesn't mean that every time that you have a derivative, every time that your derivative is equal to 0, that you're going to have a maximum minimum value, but it means that it's possible to have a maximum or minimum value only at points where your derivative of the function is equal to 0 or undefined. So that leads us to example number 5 and one more definition. And this is the important definition. I actually thought about dropping this entire section, 4.2, but this I want you to know. So this is the key of everything. Critical number. We talked about critical numbers a little bit in 4.1, but really getting explicit now. The critical number of a function is a number C, we'll call it, in the domain of our function f, where the derivative of f at that c value is equal to 0, or the derivative of f at that c value does not exist, is undefined. I'll use the same language that I did before. Is undefined. Using this now, let's actually move on to number 5. Find the critical numbers of the following functions. So part A has the function f of x is equal to x cubed plus 6x squared plus 9x plus 2. So let's find the derivative. The derivative of that function is the derivative of x squared, or x cubed, pardon me, is 3x squared plus 12x plus 9 plus the derivative of 2 is 0. So we have here, and I think we saw this in 4.1 as well. So we're going to take out, we definitely did. Yeah, we definitely used this in 4.1. Now that I've said that, I'm going to have to look back. But I'm going to say we definitely did. Let's factor this out so we can find where our function is equal to 0 or is undefined. Well, it's a continuous function. It's never undefined. So let's just find out where it's equal to 0. I'll factor out my 3. So that gives me 3 times x squared plus 4x plus 3, which can be further factored to x plus 1, x plus 3. Which lets us know that the derivative of f is equal to 0 when x is equal to -1, -3. So these two numbers here, wow, are our critical numbers for that function. Critical numbers are -1 and -3. And we'll go see if they are maxima or minima later in example number 6, but we're not going to do that yet. Moving on to part B, we have now our absolute value function. And so for part B, the function x is equal to the absolute value of x. Since it's an absolute value, thinking back, you might remember we have to have the two cases. So f of x is equal to x if x is greater than or equal to 0, and negative x if x is less than 0. Therefore, f prime x is equal to 1, the derivative of x, if x is greater than or equal to 0, and -1 if x is less than 0. Or sorry, not greater than or equal to 0, greater than 0, only greater than, not equal to. And back in 2.1 we talked about this. F prime 0 does not exist in an absolute value function. It does not exist. So therefore 0 is the only critical number. So it approaches from both sides, but never actually hits it. Zeros are only critical number because 0 does not exist. To figure out if these critical values are maxima or minima, absolute maxima or absolute minima, the easiest thing for you to do is to graph the function in your calculator and just look at it and see if it is or not. But we're going to go on the assumption now that you don't have access to your calculator, but still need to know this for some very strange reason. Maybe even kidnapped, gun to your head. You know, the old saying. Sorry for that banging of the microphone there. So if I want to find the absolute maximum and minimum values of a continuous function on a closed interval a, b, I follow 3 steps. First, I find the values of f of the function f at the critical numbers of f in the interval. So basically any critical numbers that fall within the defined interval, we check them out. I then have to find the values of the function f at the endpoints. So at the beginning and ending of the function. That is oh, forgot my t in interval. Evaluate f at a and f at b. My third step now, whoa, where are you going? My third step now is to compare your results. The largest value is your absolute maximum. Is the absolute maximum. And the smallest value is your absolute minimum. Maximum. Smallest value is the absolute minimum. And you see this information. Let's solve for example number 6. Example number 6 has us return to our function that we just derived in 5a, x cubed plus 6x squared plus 9x plus 2. But we now have a restriction. It is restricted between negative 3.5 and positive 1. If I want to write that in interval notation, I'm going to use my square brackets. That's negative 3.5 comma 1. So let's follow our steps. Find the values of f at the critical numbers of f in the interval. So our critical numbers from 5a. So from 5a, our critical numbers were negative 3, negative 1. These are both in the domain, or both in the interval. In the interval. So now we'll find them out. So now we put them into our original function. So we find f at negative 3 and f at negative 1. F at negative 3, well, that's negative 3 cubed plus 6 times negative 3 squared plus 9 times negative 3 plus 2, which through the magic of using the textbook I find has an answer of 2. And we do the same for negative 1, so negative 1 cubed plus 6 times negative 1 squared plus 9 times negative 1 plus 2 gives us a value of negative 2. That's number 1 done. Okay, we have 2 values, 2 and negative 2. We now have to compare the maxima and, the endpoints of our interval. So we'll check f at negative 3.5 and f at positive 1. F at negative 3.5, negative 3.5 cubed, plus 6 times negative 3.5 squared, plus 9 times negative 3.5 plus 2 is equal to 1.125. And finally, at positive 1, we have 1 cubed plus 6 times 1 squared plus 9 times, 9 times 1 plus 2, or 1 plus 6 plus 9 plus 2, which gives us an answer of 18. My maximum value is that one right there. My minimum value is that one right there. So that tells me absolute maximum is at the coordinate 1, 18. Or I should just say x is equal to 1. My absolute minimum is at x equals negative 2, or negative 1, negative 2. If you look on page 175, you can see a nice drawing of that graph. You might notice that since it is a cubic function with no restrictions, they would normally go to positive and negative infinity and have no maxima or minima. However, there would be a local maximum and a local minimum. But that's it. Well, we'll just leave that one at that. The last example now, example number 7, has us find the absolute maximum and minimum values of the function g of x. So this is example number 7. G of x is equal to x to the power of 2/3 multiplied by 5 plus x in the domain, or restricted, or in the interval, whatever you want to say, of negative 5 is less than or equal to x, which is less than or equal to 1. So we got to find the absolute maximum and absolute minimum value. We could do this, we could find the derivative of this using the product rule if we wanted, but why bother doing that? Let's multiply it out first. So that's 5 times x to the power of 2 root 3 plus x to the power of 5 root 3. This is going to be a little easier to derive. Oh, pardon me. That should go up here. So 5 x to the power of 2 root 3 plus x to the power of 5 root 3. And the derivative now is just a plain old derivative. Once I erase that mess there and get it back working. So the derivative, we have x, or 2/3 times 5, which is going to give me 10/3, x to the power of negative 1/3, plus 5/3, 5/3 times x to the power of 2/3. And maybe to make this a little easier, because we are trying to find the zeros, remember, or the critical values, we're going to rearrange this just a little bit. That is equal to 10 over 3x to the power of 1/3 plus 5x to the power of 2/3 over 3. I'm not sure why I'm angling so much on that. And then I'm going to multiply this one by x to the power of 1/3 over x to the power of 1/3. So I get a common denominator. So I have both under 3x to the power of 1/3. Hopefully this is sensible to you. So I have 10 over 3x to the power of 1/3 plus 5 times x to the power of 2/3 times x to the power of 1/3 just gives me x to the power of 3/3, or plain old x, over 3 times x to the power of 1/3, which now we have a common denominator. We can rewrite this as 10 plus 5x over 3x to the power of 1/3. Or maybe better put, I'll factor out the 5 first. So 5 times 2 plus x over 3 times the cubed root of x. There we go. So this is the simplified form of my derivative, and now I have to find my critical values. Remember, the critical values are when my function is either equal to 0 or undefined. It's undefined if I'm dividing by 0. So if I put the cubed root of 0 is equal to 0, so if we have 0 on the bottom of our fraction there, we're going to have an undefined. We're going to be dividing by 0. So that's not going to work. So x equals 0 is undefined. And we also will have it equal to 0 if 2 plus x is equal to 0 on the top there, or x is equal to negative 2. So if x is equal to negative 2 or x is equal to 0, we have our two critical values. So I'll write that down. Critical values are x is equal to 0, x is equal to negative 2. We also have to figure out, or let's figure out what our value of g is at those points first of all. So g at 0, so that's equal to 0 times 2 to the power of 3 multiplied by f plus 0, which is just going to give us a good old 0. And g at negative 2, so we have negative 2 to the power of 2/3. I'm not sure why I'm doing it this way. Multiplied by 5 plus negative 2, which gives us a value of approximately 4.8. And we will check our endpoints now. So our endpoints, we have g at negative 5. We have negative 5 to the power of 2/3 multiplied by 5 plus negative 5, which is going to be 0 once again. So 5 minus 5 is 0. And at g is equal to 1, so we have 1 to the power of 2/3, which multiplied by 5 plus 1, which is just going to be 1 times 6, or 6. So we have our maximum values, or pardon me, one maximum value right there, and we actually have 2 absolute minimum values. So we have 2 points in the graph where it hits an absolute minimum value. So for our function, the absolute maximum is found at x equals 1 or y is equal to 6. I guess I could write it like that. And absolute minimum, we have it twice. So we have absolute minima. The absolute minima are g at 0 is equal to 0, or 0, 0, and g at negative 5 is equal to 0. So negative 5, 0. Oh, ran out of space. Negative 5, 0. There's the edge of my board. It happens sometimes. And that is it for 4.2. So as a recap, the critical values are the places where the derivative of a function are equal to 0 or undefined. These critical values can indicate the presence of maximum or minimum values. We can check that along with an interval, a stated interval, so the domain, as long as it's an inclusive domain, or a closed interval, sorry, that's probably the better term to use, to find what the absolute maximum and minimum values are of our functions if they exist. Hopefully this was clear, but if you have any questions, please do let me know. I'll do my best to answer them. I hope you have a fantastic day, and I will talk to you later.